Welcome back. Unlike the previous lecture, we're going to probably find that this one has a little bit more math, but I don't think it's going to be anything too intimidating. Let's see how this goes, because now we're going to talk a little bit more about the energy aspects in an electromagnetic wave, or as we sometimes say, an array of light. So, first off, some important reminders here. Which of the following is true for light traveling in glass as opposed to traveling in vacuum? Is the wavelength shorter? Is the wavelength longer? Is it shorter? Is the frequency higher? Is the frequency lower? Or are two of the above correct? Think about it, make sure you know what your answer is, and let me know if you have questions at the start of class. Light is made up of oscillating electric fields and oscillating magnetic fields. Recall that we calculated expressions for the energy densities in an electric field and a magnetic field. And at the time we did them, I promised that these were going to come up again. Well, here they are. In electricity, the expression for the energy density, which is joules per cubic meter. It's like mass density, except we take the total energy and divide it by the total volume. The energy density for electricity is 1/2 times the dielectric constant, if it exists, times epsilon naught, times the square of the electric field strength, the maximum electric field. For the magnetic field, we get 1/2 times 1/kappa B, which is the magnetic equivalent of the dielectric constant. Assume that is 1, times mu naught, times B squared. And one of the things that Maxwell showed, a rather remarkable result, is that within an electromagnetic wave, the electric field strength equals the speed of light times the magnetic field strength. In other words, the ratio of the electric field strength to the magnetic field strength is equal to the speed of light. And if we play around with that a little bit, we notice that the total energy density is the sum of the energy density in the electric field plus the energy density in the magnetic field. And we have to actually look at the average values of the field strengths. So in the oscillating waves, the best expression is actually using RMS values for the electric and magnetic field strengths. If you want to put it into maximum terms, you would get 1/4 kappa times epsilon naught times E max squared plus B max squared over 4 kappa B mu naught. Recall that the expression for the speed of light determined by Maxwell is that it's equal to 1/the square root of epsilon naught times mu naught. And as a consequence, between the ratio of the electric field strength to the magnetic field strength and that expression for the speed of light, it turns out that the total energy density can be expressed entirely in terms of the electric field or entirely in terms of the magnetic field. And the total energy is equally split between in the electric field oscillations and in the magnetic field oscillations. So you can pick one expression or the other to find the total average energy density, and you can also say that you can also come up with an expression for the electric field strength as compared to the magnetic field strength. Now, measuring energy density is that's kind of an esoteric concept, and it's not something that you would normally directly measure. What can you directly measure? And the answer to that is intensity, which is basically brightness. The brighter a light source is, the more intense it is. Now, how can we quantify intensity? How do we quantify brightness? First off, the source has to have a lot of power, a lot of energy per second. So if it's putting out a lot of energy per second, it's more likely to be bright. Second of all, that light has to be focused onto a small area. So we can talk about the sun, which illuminates a spherical area, or compare that to a laser, which only focuses the light onto a very tiny area. The sun puts out gobs of energy, but it's spread out over a huge area. The laser puts out a very tiny energy, but it's only concentrated in a very tiny area. So the laser can be just as bright as the sun, assuming that the laser is pointed directly at you, and never do that, by the way. The expression for intensity is that it's equal to power over area. And we talk about average power because we are going to be looking at oscillating electromagnetic fields. So the intensity is equal to the average power divided by the area, and I gotta warn you, watch out for these symbols. Now capital I means intensity. Earlier this semester, capital I meant current. Be careful. Make sure if you write up a formula sheet to annotate your equations, make sure you identify exactly what this I represents. Now, why should you not point a laser at your eye? Let's take a look at an example. It's not out of the ordinary laser, perhaps a little bit stronger than a laser pointer, 130 milliwatts. But the thing is all of that energy is concentrated into a beam with a diameter of only 4.22 millimeters. So that's half a centimeter. That's actually a pretty wide laser beam. What is the intensity of this laser beam? So in standard units, the power is 0.1300 watts. The area that is being illuminated is circular, so we have to do pi r squared. Since we were given the diameter, we have to divide that by 2. So the area is 1.399 times 10 to the negative 5 square meters. We have the intensity, we have the area being illuminated, we divide them, and we get 9,290 with standard units of watts per square meter. Now, how bright is that? On a bright sunny day, nice summer day, the intensity of the sun at noon is 1,366 watts per square meter compared to where we are on the Earth. Obviously, if we were closer to the sun, that intensity would go up. But here we are on the Earth, 1,366 watts per square meter. So this laser, which has a very modest power, and for a laser, it's spread out over a relatively large area. It's still something like 5 times brighter than the sun. You don't stare at the sun, you don't stare into a laser beam. And we can measure intensity, and it turns out that there is a simple relationship between intensity and energy density. And once again, it involves the speed of light. The intensity is equal to the speed of light, c, times the energy density, the average energy density. So let's go back to that previous example with the laser beam, and we can ask what is the total energy in a 1 meter long length of this laser beam. So I can say that the average energy density equals intensity divided by the speed of light. 3.10 times 10 to the negative 5 joules per cubic meter. But what I want is the total energy in a 1 meter long length. Well, this is going to have a cylindrical shape. And the formula for the volume of a cylinder is the cross-sectional area times the length of the cylinder. And we found the cross-sectional area, pi r squared, and the length is given as 1 meter. And so we get a total volume of 1.399 times 10 to the negative 5 cubic meters. Therefore, the total energy, the energy density times the volume, is only 4.34 times 10 to the negative 10 joules. There's another way we could have answered this question, and that would be that the energy is equal to power times time. In this case, the time is the time it takes for the laser to spit out 1 meter's worth of laser. And since the laser beam travels at the speed of light, We can find that time. How long does it take for light to travel 1 meter? When you take 1 meter, you divide by the speed of light, and you get that the time is 3.34 times 10 to the negative 9 seconds. So then we can do power times time, and we get 4.34 times 10 to the negative 10 joules for the total energy. Now let's move on to a different topic, still related to electromagnetic waves, though, and that's the idea of polarization. The image you see on the screen with the arrows pointing away from a central location, this is representative of a beam of light that is coming straight at you, right out of the screen. It's coming right for you. And the arrows represent the direction of the oscillations of the different electric fields within that beam. There is no particular reason in general for the electric field oscillations in one beam of light to be parallel to the electric field oscillations in a subsequent beam. Each beam of light can have a different orientation for the oscillations of the electric field. So you might see one beam of light that's coming in up and down. You might see one beam of light where the electric field oscillations are left and right. You might see it from upper left to lower right. You might see it from lower left to upper right, or any possible angle between 0 and 360 degrees. It's random in general. Polarization, though, is the idea of having light in which each subsequent ray has the same orientation of oscillation as the previous one. So unpolarized light, for instance, sunlight, is pretty much unpolarized. But we can polarize light and get some interesting effects. If you have polarized light, then every single ray of light entering your eye has the same orientation for the electric field oscillations. So I just picked an orientation from the previous slide. Perhaps all of the electric fields that enter your eye have oscillations from the lower left to the upper right and back again. If all of them have the same orientation, it's polarized. I don't care what that orientation is relative to the vertical. As long as they're all the same orientation, they are polarized. It is possible to be partially polarized. We see what that might look like in the graphic on the screen, and there are a lot of situations where light is partially polarized. So there's a tendency for it to be along a particular direction, but you can still find some oscillating in other orientations. You're just most likely to find it along a particular axis. Polarizers have the ability to have unpolarized light enter on one side, pass through the material of the polarizer, and come out polarized on the other side. There are certain kinds of sunglasses that do that. Also, some kinds of camera lenses. You can see the middle picture, the same scene, the top one with unpolarized light and the lower one with polarized light, and you can see features pop out like the clouds in the sky. So there are some advantages to viewing the world in polarized light. How do those polarizers work? What we have is a thin sheet over which are laid long organic molecules. These long organic molecules are represented by the long, straight yellow lines in within the rectangle. Organic molecules are used because they're pretty cheap and they lend themselves readily to being laid out in long chains. So we imagine unpolarized light on its way from left to right, and it encounters this polarizing material. And the light that comes out is going to be polarized. Notice, though, the orientation of the light that comes out polarized. The light that comes out polarized, the angle of the orientation of the electric field oscillations is perpendicular to the direction of the organic molecules. which might go a little bit against what you were thinking. You might think that what's happening is that the light is like a cake with a file being squeezed through the bars of a jail cell. Well, it's not like that. What we have in the graphic on the bottom, the black sine wave, represents a ray of light, the electric field oscillations in the ray of light. And you see a long organic molecule, represented by the thin yellow line, and you also see a red spot that represents an electron. One of the properties of these long organic chains, aside from being long and organic, is that there will be electrons that are relatively free to move. Now, I know it makes it sound like a metal. It's not a metal, but it's not just metals where electrons can be relatively free to move. These electrons that are relatively free to move are going to be impacted by the electric field oscillations of the incoming ray. Now, if the incoming ray has at least a component of its electric field that is parallel to the organic molecule, then that electric field can exert a force on that electron. That electric field exerts a force on the electron, and the electron moves. So the electric field does work on that electron. Where's the energy for that work coming from? It's coming from the electric field itself. And so after doing work on the electron, the electric field has lost energy. And as we saw before, if the electric field has less energy, the amplitude is going to be smaller. I didn't show the amplitude getting a little bit smaller. All you see is the electric field pushing the electron in this animation. But the idea is after pushing the electric field gets a little bit weaker. And if it does it enough times, then the electric field strength that is parallel to the organic molecules is going to drop off towards zero. On the other hand, the component that is perpendicular to the long organic chains is trying to move the electrons, but it would be like trying to move the electron in a direction perpendicular to the molecule. And the electron can't move in that direction. It's constrained. So despite the fact that the electric field wants to push the electron, since the electron does not move, no work is done on it. No work is done on it means no energy is sucked away from the electric fields that are perpendicular to the organic molecule. Because we're losing energy, that means that the intensity of polarized light compared to the incoming unpolarized light is less. By what factor? And the short answer is that it drops off by a factor of 2. It drops off by a factor of 2 because even the component of the electric field that is parallel to the organic molecules, even the component drops off. The component that's perpendicular does not drop off. So an electric field that is coming in that is exactly parallel to the organic molecules, that gets wiped out. An electric field that is coming in exactly perpendicular to the organic molecules is unfazed. But an electric field that is coming in at some angle between parallel and perpendicular loses a portion of its electric field strength. It loses the portion with the component parallel to the molecules, leaving behind the component that's perpendicular to the molecules. We can find the component that is parallel to the molecules with theta. Theta is the angle between the direction of the electric field oscillations and the direction in which the polarizer allows light. We want the light that survives. So the component that survives based on this definition goes as cosine theta. Because the energy is related to the square of the electric field, we worry about the square of cosine theta. And the average of the square of cosine theta is 1/2. So that's why we get this factor of 1/2. It's an average effect over many randomly oriented electric field oscillations in unpolarized light. Half of the energy gets lost. The remaining energy is strictly in a component that is perpendicular to the long organic molecules. This observation of the light entering a polarizer and coming out with a different direction of polarization is known as Mattsson's law. In particular, let's say we have unpolarized light pass through a polarizer. It is now polarized. This now polarized light encounters a second polarizer. The light that exits the second polarizer is likely going to be less. The only way it would not be less is if the second polarizer has a transmission axis in exactly the same direction as the first polarizer. But if the second polarizer has a transmission axis that makes an angle of theta with respect to the transmission axis of the first polarizer, then the surviving light that passes through the second polarizer will have an intensity that drops by a factor of cosine squared theta. So, unpolarized light passes through a polarizer, the intensity drops by a factor of 2. That's automatic. But then, when now polarized light passes through a second polarizer, the intensity drops off as a factor of cosine squared theta, where theta is the angle between the polarized light and the transmission axis of the second polarizer. Let's take a look at an example of this effect. We have unpolarized light. The intensity is given as 250 watts per square meter, so moderately bright. And we're going to have it pass through two polarizers. The transmission axes of the two polarizers are at an angle of 27 degrees with respect to each other, and we want the intensity of the light that comes out of the second polarizer. So, the first light is unpolarized, and it passes through a polarizer. The intensity drops by a factor of 2. That is automatic. But now we have polarized light entering the second polarizer, and the angle between this now polarized light and the second polarizer is 27 degrees. So we do the incoming light for the second polarizer, which is 125 watts per square meter, times cosine squared of 27 degrees. And I calculated that to be 99.2 watts per square meter, still fairly bright. Now take a look at this conceptual question. We have two polarizers, and their transmission axes are at 90 degrees with respect to each other. So unpolarized light passes through the first polarizer, but now the polarization of the exiting light is at 90 degrees with the transmission axis of the second polarizer. The cosine of 90 is 0, so according to Mattsson's law, no light gets through the second polarizer. So if we treat these polarizers as ideal, that's accurate. But now suppose, in between those two polarizers, we're going to let those two polarizers remain fixed, but we insert a third polarizer in between them, and we make sure that the third polarizer that is in between the first two polarizers, that its transmission axis is not parallel to either of those transmission axes for the first two polarizers. What will happen to the light that gets through the combination of all three polarizers? Is it still going to be the case that no light gets through? Will some light get through, but not a lot? Will light get through as if the middle polarizer wasn't there? Or would some light get through, but the same that would get through just the first and the now middle polarizer? Think about it. Let me know if you have questions. I want to move on to a bit of a different topic that gets related mostly in astronomy. And that's the idea of the Doppler shift for light. To understand the formula for the Doppler shift for light, you have to have some familiarity with Albert Einstein's theory of relativity. And I suspect that this might not be the case for at least some of you. So I'm just going to give you the formula. And the formula says that the frequency that we observe, the frequency of the light that we observe, is equal to the frequency as emitted by the source times the square root of the following fraction, the speed of light plus the relative velocity between the observer and the source, divided by the speed of light minus the relative velocity between the observer and the source. Now, one of the things that's different about the Doppler shift for light compared to the Doppler shift for sound, the Doppler shift for sound depends upon the speed of sound relative to air. The Doppler shift for light doesn't. The Doppler shift for light does not depend upon the speed of light relative to the medium through which it's traveling. The speed of light seems to be unaffected by any medium. So we just look at the relative velocity between the source and the observer in order to get the effect of the Doppler shift. If this relative velocity is substantially less than the speed of light, maybe 10% the speed of light or less, we have a simplified version of this equation that the observed frequency is equal to the frequency as emitted by the source times the quantity 1 plus the relative velocity over c. Now, the relative velocity is a positive quantity if the source and the observer have a net motion towards each other, and the relative velocity is negative if the motion between the source and the observer shows that the distance between them is increasing. So if the distance from the source to the observer is decreasing, they're approaching each other, VREL is positive. If the source and the observer's distance is increasing, VREL is negative. Before we take a look at a problem, let's look at a property of light emitted by a typical star like the sun. Now, we've talked about the sun emitting a full spread of colors, the entire spectrum of the rainbow, plus the non-visible portions of light. But when you look carefully, you'll actually see that there are kind of almost like gaps in the emission spectrum of the sun. And those gaps are due to the presence of certain atomic and ionic sorts of materials. So we see a particular emission spectrum that gives us information about the composition of what's in the outermost portion of all things, the atmosphere of the sun. Some of these have labels. As you can see, there are some with relatively large letters, some with relatively small letters, some with no letters associated with them whatsoever. Now, I want to point out the line labeled capital C. That line labeled capital C, along with G and H and K, is indicative of the presence of hydrogen atoms in the atmosphere of the sun. And we know exactly what this wavelength is. We know it to a rather large number of decimal places because we can investigate the properties of hydrogen here on the Earth. We know the properties of hydrogen on the sun. So we know it's hydrogen. We know exactly what that wavelength is. Now, pretty much all stars have hydrogen in their atmosphere. So all stars will have a little bit of a gap at this wavelength. But if the star is moving towards us or away from us at some appreciable velocity, the Doppler shift will shift the location, the apparent location of the frequency, and therefore the apparent location of the wavelength. And when we observe that frequency, when we observe that wavelength, because of the Doppler shift equation, we have some idea of whether that star is moving towards us or away from us. Think about this question. When the sun emits a particular wavelength or absorbs a particular wavelength, maybe we look at one that is orange. So if we go back to the previous slide, in the orange part of the spectrum, you can see, for instance, this spectrum line right here labeled with a lowercase letter a. Perhaps we're talking about that one. If we look at another star like the sun, but is relatively distant, and if that same line seems to be a little bit more yellow, which of the following would describe the star's motion? So let's go back. We look at the emission spectrum of this distant star, and we see this line marked lowercase a is a little bit to the left when we look at that distant star. And the question is, how do we know if the star is moving towards us or away from us? Now, if we go back to our equation here, the wavelength is getting shorter. The wavelength that we observe is shorter than the wavelength emitted by the source, because yellow light has a shorter wavelength than orange light. It was orange at the source, it's yellow when we observe it. How does that affect the frequency? Does the frequency go up or does the frequency go down? If the frequency goes up, then this expression in parentheses must be greater than 1, and that means that VREL is positive. If the frequency goes down, that means that the expression in the parentheses must be less than 1, and that means that VREL is negative. So hopefully that gives you enough information to answer that question. Take a look at this question. The distant star shows an absorption line at a wavelength of 668.115 nanometers, but we recognize it as the hydrogen absorption line at 656.281 nanometers. We know that hydrogen on Earth, hydrogen on the Sun, 656.281 nanometers is the wavelength of that little gap. Based on this information, how fast is this distant star moving, and is it moving towards us or is it moving away from us? Now, to use the equation, we need to know the frequencies. So the frequency that we observe is based on the 668.115 nanometers, which we convert to meters. So we get the observed frequency is 4.48714 times 10 to the 14 hertz. Whereas the source frequency, same calculation, but with 656.281 nanometers, is 4.56805 times 10 to the 14 hertz. So they appear to be pretty close to each other, which is why I show so many significant figures, because we're going to have to take a difference. We're going to assume, because of the relatively small difference between those numbers, that the velocity is small compared to the speed of light. And if we plug it in, the observed frequency, 4.48714 times 10 to the 14, the source frequency, 4.56805 times 10 to the 14, times this expression, 1 plus VREL over C. And we solve for VREL. VREL over C is equal to negative 0.0177125. VREL, therefore, is that number times the speed of light, which is 3 times 10 to the 8. So we get VREL equals negative 5.31 times 10 to the 6 meters per second. Considering that 0.017 indicates that we are talking about less than 2%, therefore less than 2% the speed of light, Our approximation, the approximation equation that we used is justified. And we see that the speed of the star is 5.31 times 10 to the 6 meters per second, and the negative sign says that the star is moving away from us. This gives rise, by the way, to the idea of red-shifted light and blue-shifted light. If the star is moving away from you, we see that the wavelength gets longer. And if the wavelength gets longer, then things tend towards the red side of the electromagnetic spectrum, and we say it's red-shifted. Whereas if the frequency is shorter, we see that it tends towards the blue side of the electromagnetic spectrum, and we say that it is blue-shifted. This has some significant effects in determining the, basically, cosmology, the study of the universe as a whole. So it has some pretty interesting impact on understanding how the universe works. That's enough for now. Talk to you later.